Hello, everyone. Today we'll be presenting our project idea, Trace3D. So here's an overview of our initial down selecting process. We had everybody pitch their idea that they came up with through their individual ideation to the group. And then we had everyone rank their preference of each of the projects that were pitched. And as you can see here, we had Trace3D come out as a pretty clear winner to move forward with.
So the problem statement for Trace3D is that the maker community desires cheap, easy to use, and democratized access to high quality, excellent throughput, and durable machinery for quick prototyping. Now, one developing manufacturing methodology, which has not yet hit the consumer market, let alone penetrated into the garages and workshops of the average maker, is that of integrated electromechanical 3D printing. While the process of fabricating PCBs themselves is relatively cheap today, the associated costs of creating and producing mechanical enclosures to house and interact with digital input and output devices is often unoptimized and expensive. Combining the design freedom associated with 3D printing with printed circuit board design would drastically push the prototyping industry forward. We intend, as a team, to design and build a proof of concept electromechanical 3D printer that takes both insulative and conductive materials as inputs. The output would be an object embedded with highly conductive, low resistivity traces in 3 dimensions. With such a solution, designers would no longer be constrained by the orthogonality constraints of a traditional flat PCB. Instead, electronics can be perfectly integrated with their mechanical counterparts to fit into low-cost, compact product footprints. With a system that can additively create integrated circuit boards using cheap and readily available materials, we estimated that fixed costs, variable costs, and time of assembly will all be drastically decreased.
So the first type of market that we're looking at is the makers community, which are hobbyist manufacturers and people who love to design but don't have all of the capabilities of like a huge lab and a lot of access to other materials. So here's our first hypothetical character named Mark. He's a maker, he loves to create things, he's in the furniture industry, and is recently starting to integrate electronics into his designs and is looking for a way to integrate without using the conventionally flat PCBs in a way to make those enclosures that is not super expensive and is not super time consuming. The other type of market we're looking at are universities, especially university labs, where this could be a great use for prototyping. So here is our second hypothetical character, Keith. He is a professor of mechanical engineering and is doing research into materials and manufacturing, and really is looking for a product that will make it easier for him to test his prototypes and to create PCBs on the fly to fit his prototypes as they are prototyping.
So 6 solutions were considered for creating this product, and I'm gonna describe each one really briefly. So one solution would be to use solder wire using a dual extruder 3D printer, 1 nozzle with an insulating material, 1 nozzle used for printing pure solder. This might be the easiest and cheapest solution, but there might be issues with controlling the actual solder. Then we have solder paste, which is similar to normal solder, except the solder is embedded in some sort of epoxy-like substrate. And you can use a syringe to deposit this in layers. However, there might be resistivity issues with using solder paste. A nice middle ground to accomplish both options 1 and 2 would be to use liquid flux, whereby you have 2 nozzles and a syringe, the syringe putting down the liquid flux in between layers of insulated plastic or other material, and then the solder going right on top of the flux, thereby making it a little bit easier to control, allowing the solder to adhere to itself and removing the threat of an oxide buildup in between layers. 3 other solutions under consideration, we're using a colloidal silver mixture, which is currently what is used in some products on the market and some products that are now defunct. However, this mixture is extremely expensive and should be avoided if possible. Other options, which aren't truly to the problem that we're trying to solve, but are interesting nonetheless, are the ideas of embedded PCB, where you have a normal printer that you can embed a PCB inside of, and then have it continue and go right on top of the PCB. And then also the fragmented PCB, where you take a normal PCB, split it into much smaller pieces, and embed it throughout different places in the 3D printer, but not exactly what we were going for.
So we sought to quantify some of the main considerations of the previous 6 solutions. Main categories we consider, as you can see here, are fixed costs of the system, cost of the material, layer resolution, print speed, required post-processing, and power consumption. Cost being, really kind of the driving metric across both fixed and variable. And we assigned our best estimation for quantitative values for each solution based on our research. And you can see from the results that the liquid flux comes out first on a weighted score, with the solder paste and the solder wire following closely thereafter. We'll each present our individual visions of the leading solution. Here's mine first. Envisioned 2 extruders and a syringe, one extruder holding the plastic insulative material and the other holding the solder. And then in the middle, we have a syringe, which will dispense the liquid flux.
And my design is almost identical to that design. Only difference would be the placement of the spools of both the solder and the plastic insulated material.
My design is also pretty similar. The difference in my design is that the extruders and the nozzles are actually separated. It would take a little more like electromechanical knowledge to do this, but I also think it'd be better if we separated them so that it wasn't too much all happening together.
My idea, again, is pretty similar. The one interesting thing that I have in my sketch is a drive gear for the syringe, where the actual thing that pushes down the syringe has a corresponding gear ratio with the gear, so you can more finely control the distribution of silver paint. And then the solder nozzle and plastic nozzle, we made it of different materials associated with what's easiest to print with different materials. The build plate would be made out of copper, just in terms of material science.
So mine is the final one shown here. It fits again with the previous descriptions that we saw of the vision of the leading solution. Again, just 3 extruder heads with plastic, solder, and flux. So not much different from the rest of the solutions shown.
And so here we have a 2x2 matrix of affordability versus dimensional capability. As you can see, there are some platforms that are capable of doing 3D. However, they're always on the more expensive end. So those we have the Voxel 8 developers kit, which was actually never put into production, but was a similar design to what we have, using a silver colloidal paste and a plastic extrusion to create a 3D printed parts that had integrated PCBs in them. There's also the Dragonfly LDM, which is an extremely expensive industrial machine, but it's very capable. And then there are other very expensive and somewhat more moderately priced options, but those are both in the 2D space. So we would be looking to capitalize on the more affordable 3D space that is yet to really be filled at this point.
So this is another example showing a 2x2. In this case, we plotted print speed and use case. So as you can see on the left, these ones are generally slower in print speed, on the order of like 20 to 50 inches per minute. On the top are the industrial and the fast ones, those being the ones that we talked about previously, that are designed for industrial use. And what we are really looking to get into is that prototyping range of fast printing made for prototyping. So that's where we figure our opportunity zone would lie.
And these are just reference data that we use and some of our sources for finding those 2x2s. Other than that, thank you for listening to our presentation. That's all.